Today we shall study about the relation between field and potential in electrostatic. We consider two closely spaced equipotential surfaces as shown in figure A and B with potential radius R, V and V plus dV, delta V, where delta V is the change in potential in the direction of electric field E. Let P be point on the surface B. Delta S is the perpendicular distance of the surface A from P. Imagine that a unit positive charge is moved along this perpendicular from the surface B to surface A. Against the electric field, the work done in this process is E into delta L. These works equal the potential difference VA minus VB. Thus, mod E delta L बराबर V minus V plus delta V बराबर minus delta V. Mod E बराबर minus delta V by delta L. Since delta V is negative, delta V बराबर minus delta V. We can say mod E बराबर minus delta V by delta L बराबर plus delta V by delta L. Two conclusions. Electric field is in the direction in which the potential decreases steepest. In its magnitude is given by the change in magnitude of potential per unit displacement normal to the equipotential surface at the point. Potential energy of a system of charge. We consider first the sample case of two charges Q1 and Q2 with position vectors R1 and R2 relative to some origin. There is no external field against which work needs to be done. Work done bringing Q1 from infinity to R1 is 0. So the potential is given by V1 over 1 over 4 pi epsilon naught Q1 over R11, where R11 is the distance of point P in a space from the location of Q1. So work done bringing charge Q2 from infinity to the point R2 is Q2 times the potential at R2 due to Q1. Work done on Q2 बराबर 1 बटा 4 pi epsilon naught Q1 Q2 बटा R12. Thus the potential energy of a system of two charges Q1 and Q2 is U बराबर 1 बटा 4 pi epsilon naught Q1 Q2 बटा R12 और Q2 V1 बराबर 1 बटा 4 pi epsilon naught Q1 Q2 बटा R12. Thus V12 बराबर 1 बटा 4 pi epsilon naught Q1 बटा R1 plus Q2 बटा R2. Now the work done next in bringing Q3 from infinity to the point R2 is Q3 times V12 at R3. इसलिए Q3 R V12 बराबर 1 बटा 4 pi epsilon naught Q1 Q3 बटा R13 plus Q2 Q3 बटा R23. The total work done in assembling the charges at the given locations is obtained by adding the work done. U बराबर 1 बटा 4 pi epsilon naught Q1 Q2 बटा R12 plus Q1 Q3 बटा R13 plus Q2 Q3 बटा R23. Thus the potential energy is characteristic of the present state of configuration and not the way the state is achieved. Potential energy in an external field, potential energy of a single charge. The external electric field and E and the corresponding external field potential V may vary from point to point. By definition, V at a point P is the work done in bringing a unit positive charge from infinity to point P. We continue to take potential at infinity to be 0. Thus, work done in bringing a charge from infinity to point P in the external field is QV. The work done is stored in the form of potential energy of Q. So the potential energy of Q at R in an external field बराबर QV, where V is the external potential at that point. Now Q बराबर E बराबर 1.6 गुना 10 पर minus 10 coulomb, accelerated by a potential difference of del V or 1 volt. So Q del V बराबर 1.6 गुना 10 पर 19 joule. The unit of energy is defined as 1 electron volt. Or 1 electron volt or 1.6 गुना 10 पर minus 19 joule. The unit based on electron volt are used in atomic, nuclear and particle physics. The table shown 1 kilovolt, 10 q electron volt, 10 2 per q electron volt, 1 mega electron volt, 10 per 6 electron volt, 1 giga electron volt, 10 per 9 electron volt, 1 tera electron volt, 10 per 12 electron volt. Potential energy of a system of two charges in external field as shown in figure, q charge q1, q2 at distance r1, r2 from reference source, and the distance between two charges is r12. So work done on q2 against field due to q1, q1, q2 but upward by epsilon naught r12. Thus work done in bringing q2 to r2, q2 v plus q1, q2 but upward by epsilon naught r12. Thus potential energy of the system q1 v plus q1 v plus q2 plus q2 v2 plus q1 q2 bata 4 pi epsilon naught r12. Now potential energy of a dipole in an external field. We consider a dipole with charges q1 barabar plus q and q2 barabar minus q placed in a uniform external field. Torque tau barabar p cos e, which will tend to rotate it until p is parallel or anti-parallel to E. Suppose an external torque tau external is applied to in such a way, manner that it just neutralizes this torque and rotates it in the plane of plane, in the plane of plane from angle theta 0 to theta 1 at an infinitesimal angular speed and without angular acceleration. Work done barabar w barabar from theta 0 to theta 1 tau external d theta barabar from theta 0 to theta 1 p sin theta d theta barabar p cos theta 0 1 cos theta 1. This work is stored as the potential energy of the system cos theta 0 over pi by 2 u barabar p cos theta pi by 2 minus cos theta over minus p cos theta over minus p dot e. Electrostatic of conductor. Conductors contain mobile charge carriers. In a metallic conductors, these charges carriers are electrons in a metal. The outer electron part away from their atoms and are free to move. These electrons are free within the metal but not free to leave the metal. The free electron from a kind of gas, they collide with each other and with the ions and move randomly in different directions. Thus, we study regarding electrostatic of conductors. Inside conductor, electrostatic field is zero. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. The interior of a conductor can have no excess charge in the state situation. Electrostatic potential is a constant throughout the volume of the conductor and that this same value as inside on its surface. E electric field at a surface of a charged conductor E barabar sigma by epsilon naught R1, where sigma is surface charge density and R1 is a unit normal vector to that surface. By Gauss law, E delta is barabar sigma delta S by epsilon naught, इसलिए E बराबर sigma बटा epsilon naught. For E sigma is greater than 0, electric field is normal to the surface outward, and for sigma smaller than 0, the surface is normal to the electric field is normal to the surface inward.